So the first one, it said name 3 directional quantities. Those are position, displacement, velocity, acceleration.
Does time technically count?
No, time is just a positive number, so that doesn't have direction.
So is that a non-directional one?
Yes, you could use that for non-directional. The second one, non-directional quantities, are distance, speed. A lot of people said, like the way we talk about acceleration in speech, acceleration and deceleration. And the other one that I was thinking of was time. A few people said mass or charge. If that was like the third one and everything else was right, I gave you credit for that. But we don't use mass or charge in kinematics, so these are really the answers for kinematics. The third one, for motion along a line, how do you know if an object's speeding up or slowing down? Velocity and acceleration in the same direction or the same sign means it's speeding up. And velocity and acceleration with opposite signs means it's slowing down. And this is a really important idea because it relates to something also when we get to 2 dimensions. It tells you it's the same way to think about whether something's speeding up or slowing down when you compare the velocity and the parallel part of the acceleration vector. So this is an important idea. And one way that, one thing, sort of a trigger if you're looking for how to know what I consider important and not important, since I said this like 50,000 times, that should be like, when it clicks over to 50,000, that's when you should be like, I'm gonna pay attention to this one. This might come up again. What's the name of the mathematical object used for directional quantities in 2D? That's a vector. And if you need an intermediate variable in 2D, it's almost always TF. Any questions about any of those? Anybody have any questions about the lab exam? Yep.
So I have on number 4, my curve was and question E.
Mm-hmm.
Can you just explain it?
Yeah. What? They have different shapes?
Yes.
Oh, we need to talk about that then.
Yeah.
Oh, yeah, that's right. You got it wrong and you think it should be right?
Well, kind of, but I guess I don't know why it's...
Yeah, okay. Well, let's talk about that in lab then. Because, maybe I just made a mistake. Well, I guess now that I think about it, half of you, I did different versions for the different labs. So half of you have one version and half have the other version. But if I graded it wrong, we need to address that.
She got it wrong too, but we put the same thing. So I just, if you have...
Okay, so if it's like this,
Yeah, it's a bull shape. And acceleration is...
so this has acceleration positive.
Yeah. So it's asking for this graph to represent an object in free fall, what direction would have to be chosen as a positive direction, and how do you know?
Right, okay, so in free fall, the acceleration is downward. And so if this is a graph that shows a positive acceleration, then down has to be positive because, you know what I mean?
I just kind of thought of it as it's always up in free fall.
So in a free fall problem, if the positive direction is up, you get a graph like that. Any other questions about the lab test? Yep.
What's question 2?
Oh, so that one, it gave you all these values, and they have an average of, so the average is 9.68, and the standard deviation is 0.5. And then it asks, some of you, it asked what percentage fall within one standard deviation, some half a standard deviation. So let's say within half a standard deviation. Half a standard deviation, S over 2 is 0.25. Bless you. And so the range of values is all the values between 9.43 and 9.93. And so you figure out what percentage of your values fall in that range. And then for a normal distribution, uh, 38.2% fall within half a standard deviation. And so those are the numbers you compare. So you need to get a percentage for a percentage of your values that fall within this range, and then compare it to 38.2. For one standard deviation, it would be between, 9.18 and 10.18. And you would compare that to a normal distribution having 68.2%. So that's what I was looking for, just doing both of those two calculations, or having both of those two numbers. Any other questions about the lab test? One other one that a lot of people got wrong was number 3, where you had a position versus time graph like this. Some people had it in that direction. Some people had it with a negative slope. But in both of them, the velocity is constant, and you can see that if you draw a bunch of tangent lines, it never changes. So that means that the acceleration is equal to 0. And so the one I have drawn here is a positive velocity and 0 acceleration. And a lot of people, I think, usually when you get stuff wrong about acceleration, you're confusing acceleration and velocity. So a lot of people in this example would have said positive velocity, positive acceleration, because the values are increasing. But remember that what acceleration is a change in velocity. So if the velocity stays the same, the acceleration is 0. Yes?
Are all lab exams cumulative also?
Yes. Yep.
Explain 4C and Z.
Sure. Okay, so I'm going to do it for this one. So I guess the answers are reversed for the other one. So let me label, I'll call this A, this B, and this C. And so C asks over what interval the object's acceleration is positive. Over the whole graph, the slopes are getting more positive. And so over the whole graph, the acceleration is positive. So it's positive over the whole thing. It's never negative. One way you can think about it is anything that's concave up, like this, like part of a parabola that would hold liquid in 2D liquid, is a positive acceleration. And anything that's part of a concave down parabola is a negative acceleration. So if you had something like this, it's concave up to about here, and then concave down on the rest of it. So this is a positive acceleration, and this is a negative acceleration. Any other questions? Yep.
5 and
Okay, so 5, the one I have in front of me says plot a position versus time graph. First, of an object that's dropped to the ground from the 0 position. First with the positive direction up, and second with the positive direction down. So in both cases, what we're talking about is dropping an object where this is the 0 position. You know, that's the position equals 0. All right, so in the first case, if the positive direction is up, then the acceleration is going to be negative. It's going to start at the 0 position, and it's going to start with a 0 velocity because it's being dropped, and then it's going to accelerate in the negative direction. For the second one, it's still going to start at 0. It's still going to start with zero velocity. But this time, the positive direction is down. That means the acceleration is negative, and so it's going to look like that. Any questions about that one? Any other questions on the test? Okay. And yeah, come talk to me if you feel like something was scored wrong or I missed something you did or something like that. Come talk to me and we'll fix it. Okay, so now we're going on to the next topic. That's kinetics of particles. In 2 dimensions. And so what does kinetics mean? Well, remember, kinematics is just about describing motions. It's relationships between quantities that you could measure off of a videotape. And so it's relationships between the variables time, position, and I'll lump displacement in with position. Velocity and acceleration. But kinematics doesn't deal with the causes of the motion. It just deals with descriptions of the motion. So now with kinetics, we're getting into the causes of the motion. So we're going to combine kinematics. We still are going to use all those same kinematic quantities, but we're going to combine it with the causes of the motion. And those are force and mass. And later we'll talk about energy, but we're not going to do that right now. And so before we go on to equations that we can use to do kinetics calculations, we have to talk about what mass is and what force is. So first we have to introduce these 2 new quantities. Mass and force. And I'll do mass first because that's sort of the simpler one. Mass is a measure of an object's resistance to acceleration. The SI units of mass are kilograms. That seems a little strange. You would think it would be grams rather than the one that has this prefix that means 1,000 grams, but that's what it is. And so if you take 2 different objects and do the exact same thing to them, whatever that thing is, and one accelerates a lot and one accelerates a little, the one that accelerates a little has more resistance to acceleration, and so it has more mass. So think about a semi hitting a Yugo or whatever, a smart car. There's no people inside. Don't worry about that. Okay, so this is coming this way. This is coming this way. The force that they apply to each other is the same. The impact, we haven't talked about what force is yet, but you can think of this collision as, in some sense, doing the same thing to each of these two objects. The smart car, though, is going to accelerate a lot. It's going to, in a very short amount of time, go from almost, whatever, it's going to very quickly go from whatever its velocity was in this direction before the collision to basically whatever the truck's velocity was before the collision, right? It's going to have a big acceleration. The truck is it's only going to notice that it hit this thing if it happened to be looking, If he's on his cell phone, he'd never even know. Because the truck has big mass, big resistance to acceleration, and the smart car has a small resistance to acceleration.
So could you say that again? The bigger the mass?
The more mass, the more resistance to acceleration, the harder it is to accelerate it. So on Earth, where we spend most of our time, the way we measure our mass is with like a scale, like a bathroom scale. And that works because your mass happens to be proportional to the force that gravity applies to us. We'll talk about that more pretty soon. But so what you're really measuring is the force that you apply to the scale. And that's because of gravity. But if you're in outer space, you don't notice the gravitational force. And so like if you're orbiting the Earth and you stand on a bathroom scale, it tells you weigh nothing. You still have the same mass, but you don't have any weight just because there's no gravity. And it turns out that on shuttle missions and stuff, weighing astronauts is a really important thing because it's very easy to lose bone density when you're in space because you have a whole different set of forces applied to you, smaller forces. And so they want to weigh them accurately, but they don't have the benefit of weighing people the way we do here. And so the way that they measure people in space is they apply some known set of forces to them. It shakes them back and forth, and the thing measures the acceleration of the person when these forces are applied. And based on that, they can measure the mass. So mass is a resistance to acceleration. One thing to notice about mass is a positive number. And so that means it's non-directional. So, so it's not like you don't have a mass to the west or whatever. You just have a mass. And you don't have a negative mass. You just have a mass. So that's about it for mass. So now let's talk about force. That's the more complicated one. Force is a vector that measures the intensity of push or pull on an object. the units for force are always mass times length over time squared. Well, this can be anything, but SI units, yeah, that's the next thing I'm going to write. If you do this in SI units, it's kilograms, meters per second squared. And since force is a really important quantity in physics, you know, we're going to use force all the time. And this is sort of a tedious collection of units. So people just gave it its own name, the Newton. So 1 kilogram meter per second squared is equal to 1 Newton. And that's abbreviated with uppercase N. In this class, there are only two sources of force. Only two things can apply force to an object. Only two ways force is applied to an object. The first is gravity. And the force applied to an object by gravity is called the weight. So to us, I think mass and weight are sort of thought of as synonymous. Bless you. On a bathroom scale, you know, there's a switch underneath that lets you switch from kilograms to pounds. But we're going to have to be a little more careful than that. Pounds is a unit of force. And so if you weigh yourself in pounds, you're talking about the force that gravity applies to you. Kilograms is a unit of mass. And really, technically, the scale isn't measuring your mass. If you went to the moon and tried to use that scale, it would give you the wrong answer for the mass. It gives you a mass based on assuming that you're on the surface of the Earth, which is usually a good assumption. But it's not directly measuring the mass, you know. And then the second way that forces are applied to objects in this class is contact with another object. And so there are a few kinds of force that we're just not going to talk about in this class. There are other ways forces can be applied besides these two. And dealing with them isn't any harder or anything, but they're just not going to come up. Forces can be applied by electric fields. Forces can be applied by magnetic fields. There's probably other things, but those are two examples. We're just not going to have those. Okay, in order to express, so a force is a vector. And in order to express a force vector in components, first we need to define a coordinate system. And the reason we want to get force vectors in components is the same reason that we wanted to get position, velocity, and acceleration in components. It's easier to do math once you have it in components. So we're always, in all these problems, we're going to define a coordinate system. In kinematics, so far we haven't made any distinction between different types of coordinate systems as long as the x and y axes were perpendicular and it was a rotated version of the standard coordinate system instead of a flipped version. They were all the same. We could use a coordinate system that was accelerating, that was moving with a constant velocity, that was still. They were all the same to us. Now we have to be more careful about that. When you get to kinetics, there are certain coordinate systems that aren't allowed. So for kinetics, only what are called inertial coordinate systems are allowed. To be an inertial coordinate system, there are two requirements. First, the origin can't be accelerating. And second, the axes of the coordinate system can't be rotating. When you think about what a coordinate system is, like to make sense out of this idea, imagine the coordinate system being a video camera that's recording the motion of the objects. Okay. The video camera that's observing the motion. So what this is saying is, if you're going to do kinetics, you can't use calculations that come from a video camera that's accelerating or rotating. Okay, the video camera, it can be moving with a constant velocity, but it can't have any acceleration and it can't rotate. And I think this is sort of a gives you kind of an intuitive idea of what happens if the coordinate system is non-inertial. Funny school bus videos.
Did you say it can't accelerate
And it can't rotate, yeah. Okay. Here, this is the one. Okay, so watch this video. Okay, wait. That wasn't the one I thought it was. That's funny, though. It works the same with that one. Let me see if I can find the other one. I had one before that was clear. Oh, here we go. looks just like the other one. Okay. So, why does that look so weird? You know, it's funny because it looks weird. It looks like something happens that just didn't. It looked like something with physics went wrong. It didn't work the way that you imagine the world working. And the reason it looked that way is because just like these physics equations that we're going to use, your brain is used to doing the physics that your brain does. Doesn't use equations or whatever, but it makes predictions about what's going to happen. And your brain is used to watching things in inertial coordinate systems. And so your brain watched this scene happen where the coordinate system, this video camera, was accelerating with the bus. What happened is the bus hit a big bump and accelerated really fast. But all we saw was the point of view of the bus, of this accelerating coordinate system, and so it looked like something wacky happened that went against our idea of how physics works. And just like your brain kind of intuitively does that, these equations do the same thing. And if you tried to take those measurements that you got from that video camera, calculate velocities, calculate accelerations, and then do kinetics with those, what you would get is that the laws of physics were violated. They weren't really violated. Those measurements were just using a non-inertial coordinate system. Okay. That was funny, though, right? It's funny when people get hurt. So in an inertial coordinate system, this is the big result. Yes?
I'm sorry, what is that on number 1? Is that an O?
Origin.
Origin. Okay. Thank you.
Yeah, it's like a scripty O. So in an inertial coordinate system, you can think of force vectors being defined according to this equation. So think of a force vector as defined by this equation called Newton's second law. And we're gonna use Newton's second law all the time. I'll abbreviate it N2L, Newton's second law. And Newton's second law says F net, I'll talk about what all these mean. So the F net vector is equal to mass times the acceleration vector. So you've probably heard this F equals ma mentioned somewhere or other. And the meaning of these quantities is F is the sum of all the forces acting on a chosen object M is the mass of the chosen object. And A is the acceleration vector of the chosen object. Okay, so there's two important things to keep in mind here. The first is, of all the equations that we have and will use in this class, this is the most important one. So Newton's second law is the most important equation in this class. And then that brings up a question, like what about Newton's first law? That must be pretty good too, right? He didn't start on the second law. We'll do a lab that deals with Newton's first law because intuitively it's an important thing to understand. But in fact, mathematically, Newton's first law is implied by Newton's second law. It's like contained in Newton's second law. So Newton's second law tells you everything the first law does and more. You know what I mean? So Newton's first law is sort of like a warm-up law. He was just getting going. It was pretty good compared to the other stuff out there. But after Newton's second law, it was sort of like, thanks a lot, you know. Like I was like a big shot law for like a week or whatever until you came up with that second one. And then the third thing to keep in mind is when you're using Newton's second law, notice that when I labeled what all of these quantities are, that idea of a chosen object kept coming up. And it's going to be, and so that's sort of a key thing, and it's going to be an important thing that we're going to talk about, being very clear about what object you're choosing to use Newton's second law on. That's going to be sort of a theme. So it's very important to be clear about what your chosen object is. And one of the ways we're going to do that is using this tool called a free body diagram. And the whole purpose of a free body diagram is just to be clear to yourself, make it clear to whoever is following your work, what the boundary of your chosen body is, what's inside the boundary, what's outside the boundary. Anybody have any questions so far? Okay, so I said that the forces that we're going to deal with fall into two categories. One is the weight, and then the other one is contact forces. And so the first one, the simplest one to deal with, is the weight. How do we know what the force is that gravity applies to an object? So let's say this is the first type of force. Weight. The question is, how do we know how hard gravity pulls on objects? Well, we're going to make one assumption. We're going to make the assumption that gravity pulls equally hard on an object no matter what the object's doing. So whether the object's moving or not, we're going to assume that gravity applies the same force to it. So we're going to assume gravity pulls equally hard on an object no matter what motion it's undergoing. It undergoes. And it turns out that is the case. Gravity pulls with the same intensity on a single object, whether the object's accelerating, moving with a constant velocity, stopped, you know. So what we're going to do is we're going to use the fact that when an object's in free fall, we know what its acceleration is. And then we're going to combine that with Newton's second law and figure out what the force is. Okay? So in free fall, we know all objects accelerate downwards at 9.81 meters per second squared. So I'm going to use Newton's second law to measure the weight force of a 1 kilogram object in free fall. Well, Newton's second law says add up all the forces acting on the chosen object. What are the forces acting on the object? Gravity. So I'm just going to write that as Fx, Fy. That's just a force vector that we're trying to calculate. We have it broken up into components. There's no other forces acting on it. That's the definition of free fall. And that's equal to the mass, 1 kilogram, times the acceleration vector. That's what Newton's second law says. F equals m times a. And the acceleration vector is 0, negative 9.81 meters per second squared. I did this with the y-axis up, just like we always have done for free fall problems. And so what that says is Fx, Fy is equal to 1 kilogram times 0 is still 0. 1 kilogram times negative 9.81 is negative 9.81. And the units are kilogram meters per second squared, which is newtons. So gravity applied a force of 9.81 newtons down to this 1 kilogram object. So maybe that's the story. Maybe gravity always applies a force of 9.81 newtons to any object downward, right? So now let's do it for something with a different mass and see if that checks out. So now let's do it again. For a 100 kilogram object in free fall. Then Newton's second law says the force applied by gravity is equal to 100 kilograms times the acceleration. We know the acceleration is still the same. We've talked about that a lot. No matter what the object is, the acceleration in free fall is the same. So it's still 0, negative 9.81 meters per second squared. And so the force vector applied by gravity in this case is 0, negative 981 newtons. So this force is bigger. Okay? Gravity applied a bigger force to the more massive object. And so based on these, this makes sense. The take-home story? Take-home message? Gravity applies a force of mg acting down where m is the object's mass and g is 9.81 meters per second squared. Okay, so for really things with very small masses, gravity applies a very small force. For things with really big masses, gravity applies a big force. Okay, so if different things have different forces applied to them, how does it make sense that, so if you have a marble and a bowling ball and you drop them at the same time, this says that gravity applies a big force to the bowling ball and a small force to the marble. How is it possible that they both fall at the same speed, accelerated with the same acceleration? That seems sort of confusing. Yep.
Because the mass is resisting.
Yes, exactly. That's exactly right. So it's, again, it goes back to Newton's second law. Gravity is applying a big force to the bowling ball, but the acceleration is being resisted by the big mass of the bowling ball. And those exactly cancel out in such a way that the small force applied to the marble divided by the small mass of the marble gives you the exact same acceleration. It seems like sort of a funny circular logic, but it turns out that this idea of a force is a really useful thing, very useful in a lot of science applications, engineering applications, and this is just how it is. Any questions about that? Okay, let's take the quiz.